All right, good morning, class. We're gonna get started. I guess I should also make an announcement about homework. But first, when we discussed mass momentum energy balances, I mentioned that my lab is using mass momentum and energy balances to study what happens within living cells, and that I was giving a seminar at some point. That day is today, so you're welcome to attend if you'd like to. From 3 to 4 p.m. in WB 1250. But basically, this is some data coming out of my lab where we have tracked the velocity vectors. So these are velocity vectors of the motion of mass within individual cells. From that, and then what we would like to know is how growth, like what is the production of mass, what production of mass occurs in each little control volume within the cell. So in this case, mass is not conserved. These cells are actively increasing in size, increasing in mass. And so we take these vectors and we actually track Lagrangian control volumes as they move through the cells, right? So these are velocity vectors in an Eulerian reference frame, right? Fixed with respect to the lab. We use those vectors to track Lagrangian control volumes as they move through the cell. From that, we can see how those control volumes grow. This is increase in mass. This is the mass versus time of each one of those little boxes. You can actually see how they change mass over time. Some grow, some actually lose mass. And then from that, we can map out where within the cell growth is occurring. In this case, this is the nucleus. That's where the DNA is. And we see most activity occurring just outside the nucleus. That's the cell making protein. But this all basically comes from a simple mass balance, right? So something that we discussed in chapter 4, not for incompressible fluid, but for assuming that the cell can actually change mass and density. But it's the same stuff that we talked about. Anyway, I'll be talking about this at 4 o'clock today, as well as some other projects going on in my lab and application to cancer research. So just a note about the homework. So we do have homework due this coming Wednesday. It is a bit shorter than previous homework. So there's 3 problems. And I know, let's see, 1 and 3 are derivations, which makes them seem longer. But they do follow along in what we did in class, more or less, for derivation of a flow between 2 flat plates with the addition of a pressure gradient. And also there's a derivation given in your textbook for at least one of the coordinate systems that you're asked to solve for in problem 1, and for a similar problem to what you're asked to do in problem 3. So problem 1 is mainly about changing the coordinate system between, so you're basically going to solve the same problem in 2 different coordinate systems, and then changing the coordinate system from one to the other. And that's going to feed into a discussion we're going to have about computational fluid dynamics after the fall break. So that's why I have you doing that problem, okay? There will be a homework assigned on Wednesday, but due in 2 weeks. So there will technically be a homework out over fall break, but you're gonna have 2 weeks to do it. So you could ignore it all of fall break and have the same amount of time you normally do to work on that homework, okay? All right, any questions on material or anything else? Yes.
So with like the derivation stuff that we need to see in this textbook, are we gonna have one that solve, or
It's in chapter 4, towards the end of chapter 4. I forget exactly what section it is, but yeah, it should not be hard to find. Okay. Yeah. You know, I don't want you just directly copying that. I want you working through it and understanding why we're dropping terms out. And then you're gonna have to do it with some subtle changes and check it there as well. Yeah. Okay. Great. Any other questions? Okay. All right. So on Friday, I said we're going to do simple math on Friday. So we did k is equal to n minus j was the primary expression that we used. And we said that that would be the number of pi groups, the number of dimensionless groups that we can use to solve a problem. right? So the number of dimensionless groups K is equal to N, the number of variables in the problem, minus J, the number of fundamental physical quantities or dimensions, fundamental dimensions that we have to describe a problem, right? J is most often probably 3, but occasionally it will be different than that if we have to include temperature, or if mass, length, or time are not included in the problem, then J might not be 3. So K is equal to N minus J, tells us the number of dimensionless groups, but now how do we find them? So we're going to talk about that starting today and continuing on Friday. One approach is to non-dimensionalize governing equations or an existing solution. So if you have an equation, then we can take that equation and rearrange it into dimensionless form. So we showed when we were talking about dimensional homogeneity at the beginning of this unit, we discussed how the Bernoulli equation, by dimensional homogeneity, every term in Bernoulli has the same dimensions, right? And we could divide through, for example, by G or something, one of the variables within that equation. Every term still has the same dimensions, but now we've changed those dimensions a little bit. So you can carry that same idea through of dividing through by different constant terms to take an equation and turn it into a non-dimensional form where every term has no dimensions. And that's basically what this approach is. And we're actually going to talk about this mostly on Friday. The other approach, if you don't know what the equation is, I should have reordered these because we're going to talk about this one first. If you don't know what the equation is describing your flow, so for example, if we're talking about flow around a falling sphere, and we don't yet know really how to handle that, right? We haven't discussed external flow around objects yet. We don't know the solution to flow around a sphere. So we don't have an equation exactly describing that yet, but we do know the variables that are involved. We know the number of pi groups that we're looking for. So we can actually follow a procedure to group those variables, again, just based on their dimensions, into pi groups, into dimensionless groups that tell us something about what's going on in the problem. And so in this method, we're going to have to choose, we'll choose some primary, secondary examples. We'll explain what that means. Primary, secondary quantities, we'll explain what that means. This is the way that we're going to go through doing this in class. So we're going to designate some variables as primary, the things that we really want to non-dimensionalize, and some things as secondary. And we'll go through this example. There's another way of doing this. It's called Ipsen's method, which is described in your textbook. If this method isn't making sense to you, that we'll go through today. So this is where we're going to be, the primary thing that we're going to be discussing today. And then on Friday, we'll look at non-dimensionalizing equations, including the Navier-Stokes equations. So let's say we have a problem like we discussed wall shear stress, right, as the example that you all discussed at the end of class last time. So we have tau wall. So we know that the shear stress at the wall, the amount of viscous shear force that the fluid is exerting on a wall that it's flowing past, is a function of we said the x dimension down the object that we're considering flow over or flow through, d the diameter, we have like a round pipe, um, the mean velocity, density, viscosity, and we said the surface roughness, like the texture of this is flow in a pipe, so the texture of the pipe wall. So in this approach, what we're going to have to do is first choose some variables that we're going to designate as primary and some variables that we're going to designate as secondary. And for these primary quantities, there's a couple of rules. The first is that we need as many as there are fundamental dimensions, right? So in this case, J was 3, mass, length, time. And so we're going to need to take that list of variables and choose 3 primary quantities, one each for mass, length, and time. And these primary quantities need to have all the fundamental dimensions represented, meaning that the three variables that we designate as primary, at least one of them has to have mass in its dimensions. At least one of them has to have length. At least one of them has to have time, right, in this example. So right, in this example, our primary dimensions are mass, length, and time. So we have to make sure that mass, length, and time are all represented within our primary quantities. So these are absolute need to have. A nice to have is to choose these to be constants relevant to the problem. So in this problem, we have the wall shear stress as a function of, within a pipe, it's a function of how far down the pipe we are and the diameter of the pipe. So diameter is something that's going to be constant for our problem, right? If we're solving for a particular flow in a particular pipe, diameter is going to be a constant. And so it'd be nice to choose diameter to cover length, not x or epsilon. So diameter would be nicer. You can still get to an answer if you use epsilon or x, but it's nice to choose diameter. Yep. Generally something that's going to be constant in a particular problem. Yeah, this is one of those like dark art pieces of dimensional analysis where that's why it's a nice to have, not a need to have. You know, depending on the choices that you make for primary quantities, you can get a solution that's more elegant or something, you know what I mean, to these dimensionless groups. I don't grade for elegance, right? If I'm asking you to do one of these things. But one way to learn the nice choices is, again, through experience, which I recognize you all don't have. But it's something that I hope you'll gain some of throughout this class. Yeah, so in this case, if we want to choose a primary quantity that represents length, we choose diameter is the standard choice. All right, so the final constraint on the primary quantities is that they must not form a pi group on their own. So you must not be able to take those primary quantities and rearrange them together in order to make their own pi group among just those primary quantities. So for example, you couldn't choose, let's call this X instead of H because H is not within this problem. You couldn't choose X and D because X over D is dimensionless. And we need to, and we're going to make dimensionless quantities out of the other variables actually. So we have to make sure that these primary quantities don't form their own pi group. Yep.
So basically, they can't be like the same dimensions or inverse.
So they shouldn't be the same dimensions because then you could definitely form a pi group by just taking the ratio of one to the other, right? The inverse would be the same thing, but I mean, if you had, I don't know, if you had like an acceleration, sorry, if you had a velocity, a time scale, and a length scale or something, right? I guess mass wouldn't be represented there, but you could make a non-dimensional grouping of just those things together. So that would not work as a set of primary variables. Does that make sense?
So like X, Y,
yeah, so we'll see. So when we're making dimensionless groups, we're going to formulate, once we've chosen our primary quantities, we're going to formulate this as basically a way of choosing. We're trying to choose what those, what the powers are of every variable in our expression. And so if it's possible to make a pi group out of just the things you've chosen as primary quantities, you're not going to have enough primary quantities. Yeah, your question? Yeah, so we'll see as we go through this example. We're going to, so this is something where there are a lot of rules. I think it's best to see it by example, and we're going to go through an example on the next slide, but I want to lay out the rules first. But yeah, we're basically going to go through and we're going to say we have three primary dimensions, mass, length, time. We're going to choose one variable for mass, one for length, one for time, and then go on to the next step of the analysis. Yeah. So we have to choose one variable for each letter. I mean, you know, that your temptation might be like, let's say, replace this H with X because that really should be X. So you might say, well, if I choose viscosity, that has mass and time in it. So now I just need length. I'll use diameter, and X is easy too, right? That would be wrong. You want to because you could make X over D into a pi group. So it's possible to have a choice of three variables where some combination of them forms a pi group, and you still have all three dimensions represented. The three combined, yeah, and any combination of the three cannot be dimensionless. Does that make sense? Okay. Well, hopefully, and if that doesn't make sense to you, hopefully we can revisit that after we go through an example about making dimensionless groups. Okay. So those are our rules for primary quantities. Secondary quantities are going to be everything that's left. So all of the variables that are left in the problem are going to be our secondary quantities. And we're going to use each one of these secondary quantities to make our actual pi groups. Okay. So if we have, so we have 1, 2, 3, 4, 5, 6, 7 variables in this problem. We have 3 fundamental dimensions, mass, length, and time. So we know we're looking for 4 pi groups. Those 4 pi groups come from these secondary quantities. So that K is equal to N minus J is actually directly related to how we're going to make these pi groups. It tells us how many secondary variables in that expression. You're actually solving for how many secondary quantities there are described in the expression, and that's how those are the variables that we're going to use to make pi groups. So so let's look at this example. So we have wall shear stress within a pipe. And now the question is, what are some good primary quantities to use to describe this? So we said diameter, right? So diameter is going to be probably a pretty good one. I heard somebody else have a choice. Density. Why density? It covers mass, right? And why else? It's specific to this problem. It's generally a constant, right? In when we're dealing with one of these problems. So density is a pretty good choice. You could have said viscosity here as well. I think we're going to actually choose density. But viscosity we generally consider to be constant. It also has mass in it, but density is a good choice. Okay, so we have our length covered. We have our mass covered. We need time. What should we use for time? Yeah, velocity. Velocity is a good one. So generally, velocity is going to be like descriptive of overall what's going on within the problem. In a pipe flow problem, this is our mean velocity that we're describing here. So that's going to be a constant within a given, when we're solving it for a given flow. So velocity is a pretty good choice, right? So we'll have diameter to cover length, density to cover mass, velocity covers time, right? Notice that it doesn't have to be, the dimension doesn't have to be in the numerator or with a power of 1 or something, right? So in this case, we have t to the minus 1, and that's totally fine. Okay. And so we have all 3 covered. Okay, so now that we have those primary quantities, everything else are going to be our secondary variables, right? So we're going to have tau wall, right? The wall shear stress, mu, x, and epsilon are going to be our secondary quantities. And so this means we're going to have a pi group for each one of these in this problem. Okay. And because we've chosen our primary quantities, each one of these pi groups is going to look something like this. So pi 1, the pi group for tau wall, is going to be the ratio of tau wall to the product of our primary variables, our primary quantities, each raised to a different power, each raised to its own power. Okay, so this is the form of a dimensionless group that we're looking to solve for. So we're going to, in this case, it's going to be tau wall over d to the a, rho to the b, u to the c. And now the question is, what are the values of A, B, and C that make this dimensionless? And that's really what we reduce this problem to. We can find the powers of A, B, and C such that this pi group does not have any dimensions left, right? Such that all the dimensions cancel out. Then we will have created a dimensionless grouping of these variables. Okay, so the way we're going to do this, right? So we know for this tau wall group, we know that it has the form tau wall over d to the a, rho to the b, u to the c. And now what we're going to do is we're going to plug in the known dimensions of each one of those quantities. And we're going to basically create a set of equations for A, B, and C. So we know it needs to be dimensionless. So whatever this thing is, d to the a, rho to the b, u to the c, has to have the same dimensions as tau wall, which is mass per length times squared. So this means that, so if we just plug in, right, so these are just the dimensions of tau wall, right? So I just put the dimensions of tau wall here on the right-hand side. And now on the left-hand side, depending on what we choose for A, B, and C, the dimensions of that left-hand side will be L to the A, right? Because L is the dimension of the diameter. M per L cubed to the B. L t to the minus 1 raised to the C power. You following this? So we're doing like math with dimensions, basically. So we can expand this out, right? Or simplify this, gather all our terms together. M to the B, L to the A minus 3B plus C, T to the minus C. So this was, so if we look at the L term here, we have an L to the A minus 3B plus C. So that's exactly where this power came from. Okay, we do the same thing. M was easy here, M to the B, and T was just to the minus C. Right, and from this expression, we can see that we're going to have three equations, right? We have three unknowns. We're going to end up with three equations. We know, for example, M to the B should be M to the 1. So B has to be 1, for example. Okay. So we're going to rearrange this and solve for A, B, and C just by saying that now the exponents for each one of these terms, they have to be equal on the left and right-hand side of the equation. So for M, we get an expression that B is equal to 1. For L, we have A minus 3B plus C is equal to minus 1. And for T, we have minus C is equal to minus 2. Right. So we know C is equal to 2. We know B is equal to 1. We can plug into this expression for L to solve for A. And we'll end up with A is 0, B is 2, C is 1. Okay, and therefore our pi 1, our first dimensionless grouping in this problem, tau wall over rho u squared m. Where did D go in this problem? Exponent was 0, right? So D dropped out. We didn't need D to make tau wall dimensionless. We'll need it for some of the other variables, we'll see. But we didn't need D to make tau wall dimensionless, and we figured that out by solving this here. I saw a hand about to go up, Yannick. So the case, yeah, so the case where you would not have a solution to this, so you could have a degenerate matrix, right? And that would be if you've chosen primary variables that themselves form a pi group, then you would not have, then you would not be able to solve this problem. And then you'd have to go back and make another choice for primary groups. Yeah, if you can't find a solution to this, right, then you'll know that something is wrong. And what's wrong there is that you've chosen primary variables that make a pi group on their own. And so you have to make a different choice. Yeah. So this is an answer to the question of how do I know, right? If you had, you know, in the simple example, you chose X and D, as your primary variables, you can see by inspection that X over D is a pi group, and that was not a good choice, right? But more generally, if you have some complicated arrangement of, like let's say you've chosen tau wall, rho, and U, right? They themselves form a pi group. If you'd done that, then then you wouldn't be able to solve at this step. Make sense? Yeah. Okay. Any other questions? Okay. So now we're going to look at the second, right? So we have 1 of 4, right? So we solve for 1 pi group out of 4. So now we're going to move on and we're going to look at mu next. Right, so pi 2 is going to be based on mu. So we're going to go through and do the same process, okay? So we're going to take the dimensions of mu. And we're going to write out the form of our pi 2. Again, in terms of powers of our primary quantities. We will write out the dimensions of everything. We're going to set up a system of equations and then solve that system of equations for those powers. Okay, so same procedure. So we're going to say pi 2 is going to be mu over d to the d, rho to the e, u to the f. Okay. And so again, mu, right, we're putting here on the right-hand side. These are the dimensions of mu are mass per length time. And that has to be equal to L to the D, M to the L minus 3 to the E, L to the T minus 1 to the F. And so again, we're going to gather these up into 3 expressions. So we're going to, that's a shortcut we're about to see. So we can gather these up into 3 expressions, for L, M, and T, and solve for all those variables. I'm going to give you another, right, and follow through the same exact solution method that we did for pi 1. Another thing about dimensional analysis, though, is that sometimes if you're working with a problem, you might see a dimensionless grouping or know of a dimensionless grouping that relates those variables together. And if you do, it is totally fair to just call it out and use it. So in this case, if we have mu, rho, u, and d, certainly by the end of this class, I'd hope you start recognizing Reynolds number. And so if D is 1, E is 1, and F is 1, then this is just 1 over Reynolds number, right? Reynolds number is rho u times a length scale over viscosity. And so if you recognize that, you could just immediately say that a pi group is Reynolds number. So you can either go through the math of gathering up our variables together and solving for D, E, and F, or you can say, hey, that looks like Reynolds number. Right, this would be Reynolds number rho d u over mu, and you check and you see that 1 over Reynolds number could work as our pi group, or our second pi group. Okay. Yep.
So can I just have a matrix?
Yep. You can totally. This is a matrix solve. Yep. Yeah. So you can do this. We're doing this by substitution and all that, but you could set up a matrix solve to solve this system of 3 equations. Yeah. So this is kind of like a dark arts of dimensional analysis, right? But if you don't know it, it's fine, right? Because you can just go through the math of solving for D, E, and F. So in this case, the thing you want to check, so if we know the Reynolds number is this, then we just have to check that Reynolds number works based on our choice about primary and secondary variables. So in this case, works means that it contains just the primary quantities and mu, and that it is dimensionless. So you can't just plug in any non-dimensional number you want. It has to actually just contain the variables that you're considering. Yeah, when we're doing this type of problem, depending on the choices you make for primary quantities, you will often get a Reynolds number, because Reynolds number shows up all over the place in fluid mechanics. So either way, we're going to end up with a pi group. Pi 4 is mu over rho d u, right, which is 1 over Reynolds number. Yeah. Oh, pi 2. Yeah, sorry. I reordered these to make the discussion flow differently. You're right. This is pi 2. Thank you. Okay, so we have two variables left. We have x and we have epsilon, right? Which are going to be our pi 3 and 4, and probably going to be numbered incorrectly on the next slide. Sorry about that. So we have x and epsilon. Both of these have dimensions of length, right? X is just the dimension down the pipe, and epsilon is the roughness. That's like the texture at the wall of the pipe, which we're going to talk about quite a bit more in chapter 6. But for now, what we need to know is that it is defined as a length as well. It's like the height of the bumps. This table has a texture to it. The surface has a texture to it, and the height of those bumps would be the roughness, that epsilon variable. So both x and epsilon have dimensions of length, and so we can form pi groups by just normalizing by d, which also has dimensions of length, and that'll give us our pi 3 and 4. To get this right, x over d and epsilon over d. Now, again, this is a case where you can see it maybe by inspection, right? See that you can make pi groups by just taking those things that have dimensions of length and normalizing by d. Or if you didn't see that immediately, right, you could go through the same exact setup that we did for pi 1. Okay. You could set up the same set of equations. In this case, that set of equations would just have, the power of d would be 1, the power of rho would be 0, and the power of u would be 0, right? And so you would end up with you'd end up in the same place. Okay, there's just multiple ways of getting to the same place. Okay. Any questions on this now that we've seen an example? Okay. This is part of why I have you do that practice on, a set of linear systems of equations on homework 1, right? So it does come back in this class. All right, so let's look at another example and talk about what the results are. So let's say, yes. No. We'll talk about one of the things we can do with the pi groups. Yep. Good question. And we'll talk about it in this example of a drag on a smooth cylinder. Let's say we want to predict the drag force on a smooth cylinder. This is kind of a classic problem in fluid mechanics. We're going to talk about how to use this result in chapter 7. But let's just say we want to just generally characterize the flow around some kind of cylinder. So in this case, we're going to guess, again, from experience and intuition, or given things on a problem statement, that the drag force is a function of density, viscosity, velocity, and diameter. Right, we could have arrived at this experimentally by varying some other parameters, like the length of the cylinder or something, and realizing that it didn't really affect our results. So we end up with this this expression for the drag force. And now let's say we want to try to figure out, like, in general, how does drag force vary with respect to all of these different variables? And let's say you're going to set up an experiment where you're just going to take 10 conditions for each one of these variables. So you're going to look at 10 different fluid densities, 10 different viscosities, 10 different velocities, 10 different diameters to try to fill out this like big parameter space of, and try to figure out what the drag, how, like a general form for how drag force varies as a function of all these variables. That's 10 to the 4th conditions, right? So you're proposing then to run 10,000 experiments to figure out how drag force varies as a function of these things, which is impractical. I mean, this also in your textbook, but let's say it wasn't in your textbook yet or something. But we can learn something about this problem from pi theorem and dimensional analysis that can greatly simplify this, and it's actually what you find in your textbook. So if we use the pi theorem, we look at we start by looking at the dimensions of each one of the quantities, right? right? So we have ml per t squared for force and so on for our other variables. We recognize that we have 1, 2, 3, 4, 5 variables. We have mass, length, and time. So we have 3 primary quantities, right? So how many pi groups are there to describe this problem? 2, right? 5 minus 3 is 2. So this problem should be described in just 2 dimensionless quantities, right? So how many pi groups? N is 5, J is 3, so K is 2 with 2 pi groups. And the way that these pi groups are generally defined for this problem are first Reynolds number. So we could arrive at Reynolds number by choosing rho, u, and L as our primary variables and having mu as a secondary variable and get this pi group. And our second pi group is generally defined this way. Coefficient of drag is the drag force over rho u squared times pi over 4 d squared. Now here I should note, when you do dimensional analysis, you're not going to get these, you're not going to get anything for like a constant value in front, right? You're going to generally assume that a constant value in front is 1. And so if you were to do this dimensional analysis on your own, you wouldn't have this, 1 over, or this pi over 8 factor below. But you would still have a dimensionless group that describes the problem. So you would still be correct, right? You'd still have a correct pi group if you defined it that way. It's just that this is the way that coefficient of drag is generally defined for this particular problem, like in the literature and in your textbook. Okay. So dimensional analysis won't get you these leading constants, based on some convention that was defined 100 years ago or something, but it will get you something that still describes what's going on in the problem. Yeah. CD is what we normally call this grouping. This is coefficient of drag. Yeah, CD would be coefficient of drag. Yeah, so in this case, you could check, right? So you could check me and make sure, or check your textbook and make sure this is actually dimensionless. And I guess it better be. It should be dimensionless. And you could have also, what I'm saying is that we could have used the Buckingham pi approach. We could have used that the dimensional analysis approach to derive something that looks like this, but doesn't have this like pi over 8 constant in the denominator. It still would be dimensionless, and we could still use it. It's just that like it wouldn't match the definition in your textbook of coefficient of drag. Does that make sense? Yeah. Yeah. Again, that comes down to like the way experience and intuition and the way it's normally done. You could use mu as your primary variable instead of rho and get a different dimensionless grouping here. This is the one that's generally used in this problem. And so that's why I'm saying they're commonly defined in this way, right? But we could come up with some other definition of 2 pi groups defining this problem. Yeah. Is there another question? Okay. So we have these 2 dimensionless groups that are commonly used to describe this problem. This is written out in this weird way because normally we describe this as an area instead of in terms of a length scale, but it has the same dimensions. But if we write it out this way, then we reduce our problem to finding just coefficient of drag as a function of Reynolds number. So we've gone from one thing is a function of 4 variables to one thing is really just a function of a single variable. And this is one of the powerful things about dimensional analysis. So we've reduced the number of variables that we have to consider in order to understand what's going on in this problem. So instead of 10,000 experiments, we get the same coverage with just 10. Or more realistically, we're going to run more than 10 experiments, but we're going to use that data more intelligently, right? We're going to use that data to get a more general idea of how coefficient of drag varies. Yeah. The force of drag is I mean, this expression says the force of drag is 1/2 CD rho U squared times A. So for the same rho U squared times A, yes, it's proportional to CD. But we'll see that like coefficient of drag is a function of Reynolds number. So if you change U, right, then you also change Reynolds number. And so there's some link between the two. But it is captured entirely by this functional form. Coefficient of drag is a function of Reynolds number. Sorry, was there another question? I saw another hand going up. So what we would predict based on this is that if we look at real data for drag around for drag force on a cylinder, and we plot it as not as drag force versus all those variables. We plot it as coefficient of drag versus Reynolds number. We should see a single line. That's really what this tells us. It doesn't tell us the shape of that line, just tells us that there should only be a single line. And when we look at real data, right, this is what we see. So this is coefficient of drag as a function of Reynolds number. And this is across orders of magnitude in Reynolds number, right? This goes from Reynolds number 10 to the -1 up to Reynolds number 10 to the 6, and it really keeps going. And these data points in different shadings are all from different experimenters, right? Different labs over decades. But when expressed in this way of coefficient of drag as a function of Reynolds number, they all fall on one line. Now this line has a weird shape, right? Dimensional analysis doesn't tell us the shape of the line. All dimensional analysis tells us is that because coefficient of drag is only a function of Reynolds number, there should just be a single line here. Okay, and so that means that now I could go out and design a set of experiments where, for example, I just change Reynolds number, measure coefficient of drag, and add new points to this line to figure out what the shape is. And so this dimensionless or analysis or dimensional analysis allows us to like capture a huge range of behaviors, right? And show that this huge range of behaviors is all described by a single line, right? So it tells us something really fundamental about everything from, so this is what flow at really low Reynolds number around the cylinder looks like. And we see it's symmetric on the front and back side. This we would describe as creeping flow. It's like ultralaminar flow. We'll see some examples and videos of this as we move through the class. But we have this, this kind of flow is on the line. As we increase Reynolds number, we have something that looks still pretty similar to that. We increase Reynolds number again, we start to see some asymmetry front and back. There's actually a small wake forming behind this, but again, it's on the line. We increase Reynolds number, we now have something, we now have a real large wake forming behind the cylinder, but the drag coefficient of that is still described by the same thing, or still described by the same dimensionless form. And as we increase Reynolds number even further, we can start to see turbulence, the formation of a turbulent wake. In this case, now we're in a fully turbulent solution. And again, it's described by the same scaling law. Okay, so this is one of the ways that we can use the, and this is one of the primary ways that we're going to be using the results of dimensional analysis in this class. We can take a problem with a whole bunch of variables and boil it down to just the minimal number of variables that we need to actually describe what's going on in that problem. And then that gives us an approach to take something that's complex, right? This is massively complex, right? All the behaviors that are going on here. But say something fundamental. In this case, we said that the drag force expressed as coefficient of drag should just be a function of Reynolds number. And so there's just a single line here, right? And if I want to predict drag force on a cylinder, I just have to make measurements at different Reynolds number, plot it this way, and then now I have a coefficient of drag that I could use to back out the force on the cylinder at that particular point. Does that make sense? Some sense? Yes. So if we had a rough surface, yeah, so what would happen if we had a rough surface? So exactly, that's exactly the case. So if we had roughness, right? So we said smooth cylinder, right? Let's very careful to say smooth cylinder. So if we had a roughness, if the cylinder had some epsilon, right? Then we would have one more variable. Let's just go back a slide. 2 slides. Okay. So if we now had drag force, right, for a rough cylinder, the function of rho, u, v, d, and epsilon, right? So we added another variable. Now n would be 6. We still have 3 dimensions. So we now have 3 pi groups to describe this problem, right? And those pi groups would probably be defined as Reynolds number, coefficient of drag, and that non-dimensional roughness epsilon over d. And in that case, now if we go to, if we were to try to plot it, we would actually have a series of curves, right? We'd have something, so this would still hold for smooth cylinder, right? Epsilon equal to 0. But we now have other curves describing the roughness, sorry, the coefficient of drag is a function of Reynolds number for different roughnesses. So we have a higher dimensional function describing this whole problem. That makes sense? Okay. Yeah.
So then pointed out function of Reynolds number. Without that being pointed out, how did you?
Yeah, that was the result of our dimensional analysis. So we said originally the problem was drag force is a function of our 4 variables, right? And what we're trying to do in some sense with this kind of dimensional analysis is figure out the functional form in terms of the non-dimensional quantities. Yeah, so and this one, so we made our coefficient of drag. So another thing to maybe take away from this is that generally the thing that's on the left-hand side, right, that we're say something is a function of other things, right, the variable on the left-hand side, we normally reserve that as a secondary quantity. So we normally make a non-dimensional quantity out of that. You can get a solution, I mean, even if you don't, but we normally say the thing on the left-hand side is a secondary quantity, so we don't choose it as a primary quantity. And then we're going to end up with that thing as a function of the other non-dimensional variables. Yeah.
So in this case,
So roughness would be another independent variable, right? So we'd have to increase the number. Would be another independent variable. We would not be increasing or changing the number of dimensions, right? Because we still have MLT. And so we'd end up with coefficient of drag as a function of Reynolds number and epsilon over d. Okay. And then when we went to run our experiments, we would now have to vary both Reynolds number and epsilon over d. Okay, yes. Yep. This is why we have, so the question is this why we have so many charts in engineering that are, non-dimensional like this? And that involve where the chart themselves involves an equation for each one of the axes, right? That's the result of dimensional analysis. So in chapter 6, we're going to talk about flow in pipes. We're going to get to know the Moody chart. It's going to describe the coefficient that describes the frictional losses within the pipe as a function of Reynolds number. And we're going to have a series of curves for different roughnesses because it's the result of the same kind of dimensional analysis. Yeah, and in heat transfer, right, you're going to see this, you see this all the time. All over the place in engineering, you see the results of dimensional analysis, and this is where that comes from. Okay, this kind of thing. All right, any other questions on this? All right, I'm just going to introduce the thing that we're going to talk about on Friday after videos, which is, let's say we do know the equation. So that was what we can do. Even if we don't know the equation, right, we can simplify what we have to do in the lab, right? We can simplify what we have to do to get an empirical relationship between variables. But if we know the equation, we can do something as well. Yep. Oh, sorry, Wednesday. Yeah, that's right. I lost track of time. Wednesday, we're going to pick this up. That's good. We have an extra day even before break. Yeah, so Wednesday, we're going to pick this up. Sorry, not on Friday. Wednesday, we're going to pick up with non-dimensionalizing equations. I've been working all weekend. I forgot what day it is. Thank you all. See you on Wednesday.